All right, so the talk I'm going to give today is dealing with exploring a new concept of exploring the coupling between within Geospace. And while I'm presenting it, only my name's up here. A host of people in the community have been involved in this, many of which are at this conference. And this has kind of been born out of a discussion about trying to establish a capability of imaging the contextual, global scale ionosphere and auroral regions. So the new concept is basically named Geospace Dynamics Observatory, picking off a little bit from the existing Solar Dynamics Observatory, which provides some fabulous data of the sun in many wavelengths and very high resolution. And this would do the same thing for Geospace. And so the Geospace Dynamic Observatory would basically take advantage of an existing asset, and I'll talk a little bit about that here in a second, by orbiting a very large telescope at very far distance away, basically at a lunar distance, but you'd put it in a polar orbiting circular orbit. Basically, it would have a 27-day period. So as you are orbiting the Earth, you would be looking down from a rather great distance, but imaging the full disk at the same time with incredible spatial and temporal resolution. That means you'd have fantastic sensitivity to be able to observe many of the emissions that we've seen on smaller missions that have provided us a lot of information about astronomy as well as the aurora, but be able to do it in a way that, one, you would do the entire disk at the same time, but also you would increase the sensitivity, that is the time rate and the spatial resolution. Nominally, one would imagine having a three-channel ultraviolet imager looking at some of the key emissions in the LBH and 1356, an extreme ultraviolet imager to observe the plasmasphere. This would be a separate instrument, and then a spectrometer which would share the focal plane with these three-dimensional imager. I'll give you the summary very quickly here just to let you know where I'm going with this, is that the motivation for this is that this would provide a key link in the coupled sonar system, in the sense that you would be essentially imaging this TV screen, as Tom mentioned earlier, with incredible capability. It would address a little bit more of an applied component, where it would be filling the gap of some space weather capability to enable some predictive aspects. And it's also consistent with the recently released decadal survey in the sense that there's a strong emphasis on investigating the coupled system in geospace, and many of the notional missions that are called for there call for some imaging, and this would essentially fill the bill for every one of those. The other interesting fact is that this would be not like your typical PI-led instrument or even missions that we've had, but it'd be more of an observatory class, more like the great observatories in astrophysics, in the sense where people would propose to use time on it. And that's kind of the idea. Here's kind of a pictorial diagram just showing the orbit, where you would have it's a three-axis stabilized spacecraft pointing nadir. This is this piece right here actually exists. And one would have to build the spacecraft and the propellant and the instrument base, which sits inside this area right here. This right here, as you may have seen, been made aware before, is that this is one of the optics that the NASA was gifted from the National Reconnaissance Orbit. So this is basically a 2.4 meter telescope. Basically, imagine Hubble looking back at the Earth. And that's what we're talking about here. So this is just way beyond anything that we could have imagined before, or we could have imagined, but we just did not think in those directions. This is bringing to bear a fabulously capable asset onto our science. So I had to throw this in here just because everybody has this figure, and so this is Geospace. And this is a very complex interface of the magnetosphere with the with the ionosphere, and the ionosphere with the lower portions of um, the upper atmosphere. And the point I'm trying to make here is that this is an incredibly complex system, as people have been talking about all along. And being able to observe it in a very unique way will undoubtedly give advances to significant science. And three areas that have been identified along those lines are basically provide a very, very probing aspect of looking at the upper atmosphere, and as well as how it responds to the sun and how it then impacts the auroral emissions and the aeronomy emissions that take place. The second one would be looking at waves and tides that come up from below and how that impacts the distribution of the variability in the ionosphere, and one could observe that on very long time scales but with very high sensitivity. And the third one is that there's been a lot of discussion about ion outflow and from the atmosphere, and there's a possibility that with this incredible capability that we could actually observe that, image the emissions of those constituents as they are exiting and heading down outside of our atmosphere. So the concept, again, just remind us, is that it would be a near solar or circular orbit with a set of instruments. This plot right, or this table right here, just kind of gives a little bit of sense of comparing the capability of an asset like this relative to other spacecraft and missions that have been flown. In these columns right here are missions that have been flown, and many have been on spinning platforms. The polar spacecraft had a de-spun platform. I didn't mention the vis imager, but I mentioned the ultraviolet imager here. And then these are concepts that have been proposed, which are many of which are on spin-stabilized platforms as well. Actually, these would be three-axis stabilized, not spin. That's an error right there. And I want to draw your attention to the last column here, which is the Geodynamic Observatory. And there are a couple of places that I kind of highlight. This first one is the image cadence, where we've had image cadence on several seconds or many seconds. The capability here would allow us to do 1 second cadence. And then the spatial resolution, we've had multiple kilometers, 50, 20. Some of these are actually quite generous. We have had some rather high resolution. This has the capability of going down to less than 2 kilometers. And then lastly, just the sensitivity. If you look at the photons per second per Rayleigh per image, you get a sense of the typical state-of-the-art that has been flown, and this goes up by several orders of magnitude over some of these, or at least an order of magnitude. So not only does this have very high temporal resolution, spatial resolution, the sensitivity is unparalleled. Just to give a sense of what we could be looking at with this, these are data from many different spacecraft, DMSP, some imaging the bands, equatorial bands with image, as well as some of the GUVI instruments in looking at the same thing, looking at the very dynamic aspects of it. Even our earth science folks have, on the VIRS instrument, measured the aurora as contaminant for their cloud cover at nighttime. But nevertheless, many people are capable of seeing the aurora, but it's all either a very average, or you have to pull in orbits, or it's a single composite, and you're not actually just staring down there and looking at it for a very long time. I call your attention to this image right here when it goes back to the aurora, that this would be typically the resolution that we'd be looking at. VIRS has a resolution of about 1.5 to 2 kilometers, and this is what we would be looking at. But imagine that across the entire globe, 24/7, for weeks at a time. We do have the capability of, we do have data showing the dynamic aspect of the aurora and other emissions. From Steve Mindy's FUV imager on image, we imaged the Bastille Day, fabulous data. You can kind of get a sense of the time resolution and the spatial resolution. On Themis, they have the ground-based network, and this is, I think, what Tom may have been referencing also, where you give quite a bit of very good resolution. Of course, these would only be useful at nighttime and on clear sky, but nevertheless, you can get a sense of what's possible here. The Geodynamic Observatory would be providing resolutions like this, except that over a continuous basis, not worried about cloud cover or visibility. This video I'll show very quickly here, but you may have seen this, but this kind of gives a sense of the power of such a mission like this in terms of capturing the human imagination and really pulling in young scientists for our future. One can imagine that these sorts of resolutions, again, this is the type of resolution we'd be talking about. Of course, this is just right almost on top of it. We would be looking at the full disk. Not only the full disk, though, but as you image the disk from such distance, you also get the limb. So you would get nadir viewing of the disk simultaneously with limb observations. With the spectrometer that you would have here, you could look at spectra. You could look at a height altitude as a function of emissions, an incredibly powerful capability. The mission characteristics, I've mentioned some of these, but basically it'd have a pointing resolution about half a kilometer with an accuracy of 0.1 arc second. Nothing here is really stressing any technologies. I have multiple sensors. One of the issues is going to be large bandwidth. If we go with 1 kilometer or to 2 kilometers, we're talking about 11 terabytes a day. That's a ton of data. Obviously, that's assuming you bring everything down, and you'd have to look at compression schemes and that sort of stuff. The telescope characteristics, I've mentioned most of this. The sensitivity would be about 100 Rayleigh per 1 second image with a signal-to-noise ratio of 5. Here are some nominal wavelengths that I've identified there. And then going to the summary again, is that a mission like this, albeit not cheap, would be incredible. It would provide help us understand this coupled link. It would open a window of discovery that we simply do not have access to right now. It would probe emissions, the aeronomy, and the auroral emissions in a way that we just have not been able to do before. It would help in our space weather endeavor to provide a stronger, robust foundation for predictive capability. As well, it is consistent, certainly in the science theme, that the nation has put forth for our space agencies to go after. So with that, I will close, and I've got more backup material, but I'll just leave it at that.
You got a microphone?
This is the question is, was this in the decadal? This was probably closest reflective, I think, to the Medici mission, which is one of the top 4 notional missions recommended. However, I would point out that at least 3 of the 4 top missions that were identified in the decadal all called for contextual ultraviolet imaging, Medici being the predominant one. And so one of the ways, in my own mind, of justifying spending so much money is that this would essentially cover the science that several of those missions would do, enabling a less expensive implementation of the balance of that science.
When the NRO transferred those telescopes to NASA, I believe they did so with the condition that they never be pointed at Earth.
That's a very good point.
Does that have any implications for your mission concept?
Yes, it does. We've explored that quite a bit because that was one of the very first things we were going, oh my goodness, it's a showstopper. So I would point out two things. One is we actually cannot image the surface of the Earth at these wavelengths. So the second is that the distance and the resolution that we have, while I would consider it phenomenal, it does not violate the issues that they were most concerned about. And the third thing is we're not even allowed to speculate on anything, and so I'm not going to say anything more. But I think we're okay on it. We got kind of clearance from headquarters on that.
Is there any reason not to include ENA imaging?
No, there is not. I did not have that on my first. This is a large telescope. Clearly, the ENA would not take advantage of the large telescope. One of the things that we strongly considered, we put the plasmaspheric imager, the EUV, as kind of a set aside on the side, not using the same optical train. We would do the same thing with ENA as we got, if this began to get legs and we really pulled together the strong scientific justification for it. I think imaging all of Geospace, including ENA, would be critical for that.
Jim, I think there's some really important capability that's missing from your presentation that you might want to add, I think.
Okay.
That is that the increased cadence and sensitivity of these observations brings data visualization and image processing techniques into the arena of space science, so that for example, these repeated cadences allow you to identify gradients in the air glow from both ions and neutrals, which allows you to derive things like bulk dynamics of the gases and the ion motions, not just contextual pictures.
Understood. And I recognize that I have not done the science justification here, and there are people who are much more expert to be able to really pull the physics out of that needed there. But thank you. I'll give you a call.
A really interesting mission concept. I wasn't going to say anything, but once ENAs were mentioned, that there's another capability that's worth considering in a mission of this type, if not, this one, and that is it would be neat to image the magnetopause cusp region,
yes,
if you wish, the solar wind plasma as it flows around that thing, particularly in conjunction if you're also having a plasmaspheric thing, and there's a way of doing that with
is that
soft
Thompson scattering?
X-rays.
Oh, the soft X-rays. Okay.
Soft X-rays, yes.
Okay.
Yeah.
All right. Well, let's talk later because I've got some ideas
Yeah.
on that. Thank you. Hey, Mike?
Yeah, with 11 terabytes a day, you're going to put SDO to shame and need some serious data mining and visualization. My
yeah.
question, though, is you mentioned observing time requests. What if you're just pointing at Earth? What's the need for special requests for observing time? I don't understand.
Well, you're right, and clearly there are some. There may be different modes that we could operate this. For example, the data crunch may require to operate some things full bore at one time and other times at a less reduced level. You're right. If it's not doing any extra pointing, but there is some thought that you might want to point down the tail at certain regions to look at outflows. Yeah, or the magnetopause, right.
Okay, are there any other questions? So I guess.
All right, I would just make one request. Just send your checks made out to NASA for this, because it's not going to be cheap. And I'll let Dave field those questions.